Hi everyone, today I will present our research named Shape Correspondence based on Kendall shape space and RAG for 2D animation. I'm Liu Shaolong from Beijing Normal University, and this research was collaborated with Professor Wang Xingce and Professor Zhongke from Beijing Normal University and Professor Seah from Nanyang Technological University. Well, before I pursued my PhD, I'm a digital artist in the field of animation. Through a period of work, I realized that even now with computer support, some production processes in animation are still time-consuming and labor, especially in 2D animation, like in-between, coloring, and so on. If you observe these processes, you will find that they are all based on the correct correspondence. So if we can propose a digital correspondence approach that can improve the accuracy and reduce the computational complexity, maybe we can save the animator's time. So that is our motivation. But solving this correspondence problem is very hard. The difficulties are that the 2D animation shapes usually deform heavily because of artist creative drawing. The topology of shapes also may be inconsistent due to partial occlusion, like this figure shows. So to sum up, the problem is difficult, and that's why after all these years, it's still a hard topic. We decided to start with region correspondence. The previous methods can be roughly classified into three categories that are methods based on geometric attributes, local topology, and global topology. However, their shape similarity matrix is only sensitive to local geometric features, and it is not robust to similarity transformation. Or they rely too much on local topology and parameters. In addition, they may fail when the topology is changed strongly and the user also needs to input more keyframes for correspondence. So to address these problems, we introduced a 2D vectorized shape correspondence method based on Kendall shape space and the region adjacency graph. Therefore, our contribution can be summarized into three. The first is to propose the region correspondence framework for 2D animation. The second is we introduce a Kendall shape space model in region similarity measure. The third is the region adjacency graph, aka RAG, is introduced to associate the neighbors of the corresponding regions and match shapes. Our method can efficiently find the correspondence of regions with exaggerated deformation and unstable topology. Besides, it is also robust to the similarity transformation of shapes. So for this correspondence problem, we propose a framework with four models. First, the topology and the geometry representation models. It can translate the input shapes into the local topology and the geometric information for framework. The region similarity measure in Kendall shape space model can calculate the similarity of the different regions. The local adjacent region matching model can find the correspondence between two local adjacent region graph and propose region pairwise candidates to the next processing. And the globally optimal shape matching model can optimize the computational complexity and extract the final correspondence between two shapes. So let me introduce the construct of our framework first. Assume we have two different vectorized 2D shapes. First, we construct RAG by the first model. Then, with RAG, we run the fourth models until the optimal region correspondence is found. In this process, the third model is called interactivity, and it requires utilizing the region similarity in the second mode and the topological information provided by the first model. Now let's take a look at each model. The representation model is the fundamental of our method. Let's start with the topology. In our paper, region adjacent graph, we call it RAG, is introduced to provide the topology information. RAG is a kind of attributed planar that can be denoted as this equation, where VR represents the regions in a shape. E represents the relationship between two regions. A, V, and AE represents the attributes of VR and E. The RAG can reflect three kinds of relationships. The adjoint relationship means that there will be a shared boundary between the two regions. The boundary can be a stroke or just a vertex. The interrelationship can be described as a region wrapped in a bigger region without a shared boundary, like the eyes in the figure. The separated relationship, there's no boundary. For geometry representation, the regions are made up of the contour that can be represented as a set of sequential strokes capable of forming a closed curve into the animation. The definition to depict a shape is a finite number of landmarks on the contour of the region. A mathematical representation of source region C and target region C prime can be expressed as a 2M vector, as the equation shows, where M is the number of contour points, X and Y represents the position of the contour points. So the next model is the region similarity in Kendall shape space. The Kendall shape space is a quotient space of R2M, and with the quotient topology performing on Riemannian manifold by isometric Lie group action. The similarity measure based on Kendall shape space can show the intrinsic difference between two shapes. Therefore, our metric of similarity is robust to similarity transformation, and the similarity distance is more accurate and sensitive to shape deformation. But how to calculate this similarity? There are three steps in our method that are: first is constructing per shape space and calculating the geodesic distance. Then finding the start point of the contour. First is constructing per shape space. Assume we have two contour points at C and C prime. Constructing pre-shape space means to remove the translation, scaling, and the rotation between C and C prime. For removing translation, we extract the centroids of C and C prime and move the centroid to the other until they overlap. For removing scale, we calculate their scale according to this equation and scaling one of them by a transformation metric. After removing translation and scaling, we calculate the rotation angle and then use the rotation metric to rotate one of the shapes. After constructing the per shape space, we can calculate the distance, geodesic distance between two shapes, and visualize the shape space as 2M, as this figure shows. The two contour points size are embedded into a 2M dimensional sphere as points VA and VB. M is the number of contour points. Geodesic path between VA and VB in the shape space is an arc on the S2M. By calculating the geodesic distance, the similarity of two regions is obtained. But Kendall model requires C and C prime be in one-to-one correspondence. In other words, the the model is sensitive to the number and order of contour point sampling. To meet this requirement, our method is to fix the starting points P of C and iteratively set the start point P prime of C prime. On each iteration, we calculate the objective function f between C and C prime until we find the smallest value. This is the whole process of our algorithm, and we skip this part to save time. If you are interested in this, you can find it in our paper. Well, the next model is a local adjusted region matching model, aka LARM model. This model's function is that if we have to match regions with their neighbors, we can find the correspondence of their adjacent regions. In other words, we can find the correspondence between two local adjacent graphs. So what is a local adjacent graph? Local adjacent graph, aka LRAG, we can see it as a subgraph of RAG. Any nodes in RAG and its adjacent nodes can form this subgraph. Like this orange pens and its neighbors. The orange pens in this RAG is represented as a V man, and its adjacent nodes are represented as a V neighbor or VNB. E prime represents the relationship of the region, which is to share at least one edge or point. The next task we need to do is find the correspondence of adjacent regions. Assume we have to match main region Vmain and Vmain prime, like the two pens. We need to establish correspondence between their neighbor regions. We regard the problem as a weighted bipartite graph matching problem with a minimal matching cost. The cost metric consists of the similarity between two regions from two LRAG. So we compute all the shape similarity cost between neighbor regions, and we use the KM algorithm to solve this assignment problem. The key of constructing this metric is how to define the weight value on the edge. In other words, how to define the similarity between the neighbor regions. So we propose the neighbor region similarity calculation for adjacent region matching as the follow equations. Here the S represents the similarity. The union of Vmain and VNB represent the shape of the region after the main region and the neighbor regions are merged respectively. Lambda is the corresponding weight coefficient. As this figure shows, assume the two pens have been matched. If we want to get the similarity of the orange shoes, we need to merge the pens and the shoes first and then calculate the similarity using Kendall model. The advantage of this method is that the geometric attributes and the topological attributes such as the relative position of a neighbor region and the main region, the relative size, the boundary length, and so on are implicitly included in the merged shape. Here, when we merge the two regions, we need to consider their boundary types. The boundary of the two regions can be categorized into three types as the figure shows. We need to standardize the rules for sampling in the different types. Then we propose the globally optimized shape matching method, aka GOSM, based on the heuristic RAG search and correspondence global optimization. With this method, we can exploit the global topological information to ensure accuracy and reduce time cost. There are three stages in this method: the seed region initialization and RAG heuristic traversal, and candidate regions matching. Assume we have two RAGs from source and target shapes first. We will find the seed regions of them. That means we will select the starting node of the traversal. Note that the selection of seed regions will directly affect the accuracy and the efficiency of the algorithm. So the seed region should meet some conditions. Then after the seed regions are formed, we begin the traversals of the two RAGs. We traverse the two RAG at the same time, where we utilize the heuristic BFS or DFS algorithm as figure shows. Starting with the seed regions, each time we visit a new node, respectively, two new LRAGs will be generated, then the LARM models will be called. After LARM processing, the adjacent nodes will be given a cost. We find the adjacent nodes with the lowest cost as the next nodes to visit and repeat the above procedures until all nodes are visited. After traversal, each region will have several matching candidates. The final stage is constructing the one-to-one region correspondence from these region matching candidates. We use the KM algorithm again to find the global optimal correspondence for all the regions. For the inner regions, we regard this as a new shape and reuse our method to construct the correspondence. To test our approach, we did two experiments for cartoon hand-drawn cases. The first experiment shows the results of shape's correspondence accuracy and time consumption. Under three different situations, which are using only Kendall shape metric model, use Kendall shape and ARM model, and use all models in our method. The results show that our framework is capable of can combine the models to match the regions for the cases in abrupt deformation and topological inconsistency. As mentioned above, we can find that even the cases have more than 90 degrees of rotation. The method still got a good result. The second experiment shows the comparisons with existing classic method. We compare with the sheep contact method, choose method, and juice method by our cases. Generally speaking, our method obtain better results in terms of accuracy and time consumption. So, in conclusion, in this paper, we proposed 2D vectorized shape correspondence method based on Kendall shape space and the RAG. It can fully utilize the geometry, local and global topology of shapes. Our method is good at handling situations where shapes with exaggerated deformation and unstable topology. Besides, the translation, rotation, and scaling of the shapes will not affect the accuracy of the shape correspondence in our method. Many convincing results are obtained and indicate our method outperforms the existing methods when the cases have the condition we mentioned above. However, our method still have limitations. Our method cannot handle one-to-many or many-to-many correspondence situation. For example, as the figure shows, if region 1 is split into 2 and 3, in our method, region 1 can only correspond to the region whose shape and topology are more similar in 2 and 3. As for future work, we expect to work on the limitations and explore stroke or intersection points correspondence based on our current work. We hope that our approach will help animators improve their productivity and create more works for us. So that's all. Thank you. And for more details of our study or algorithm, please share this paper. Thank you.